Hello, my name is Malcolm Griffiths. I'm retired from Chalk River Laboratories and I'm adjunct professor at Queen's University and Carleton University in Ontario, Canada. I'm going to share with you today some of my thoughts on diffraction in the TEM based on the accumulated experience I've had during my career. What I've done recently is created a book, An Engineer's Guide to Nuclear Reactor Core Materials. And in chapter 4 of that book, I talk about characterization of microstructures. And I didn't want to get into too much detail when it comes to the theory of diffraction in the TEM, especially the TEM, although I do cover X-ray diffraction quite extensively. I make the point that transmission electron microscopy using electrons or electron diffraction is more complicated than X-ray diffraction because of the interaction of the electrons. They're charged particles, waves that interact much more strongly with matter than do X-rays. So I thought I would follow up and actually give you my thoughts on electron diffraction and how it should be treated. Okay. All of this can be picked up if you read these books. Hirsch, Howie-Whelan, Nicholson, and Pashley. I've taken a liberty here and rearranged the names because I can then call it HHWNP, which is as it was introduced to me when I was a student. More recent book, which essentially takes a lot of what these guys developed back in 1965, apologies, back in 1965, and adds more to it in the context of modern times with modern equipment and advances in understanding. So it takes a lot of what these guys did and puts it in a new book. It was published in 2009. I think there's a second edition out in 2016. I'm not sure. But Williams and Carter, that's a very good book to refer to. And when it comes to defect analysis, my old supervisors here, Loretto and Smallman, they produced a very nice book which is useful for students of electron microscopy who only want to use the fact that diffraction occurs or Bragg diffraction occurs in order to analyze microstructures. Oh, here we go, Bragg diffraction again. Oh, I think this is where, because I'm starting to get more into the theory. Again, just a reminder what Bragg diffraction is: simply superposition of the waves for different conditions, angular orientations of the incoming and outgoing waves. So, okay. Move a little bit off now, more to do with diffraction in the TEM, which is related to the TEM itself, not so much the material. So we're going to, but it's still the same principles. Superposition still applies. And what you come across when you're imaging or doing defect analysis, there is a thing called Fresnel, which is the near field diffraction effect, and Fraunhofer, which is the far field. So what we're simply looking at, if I can demonstrate with respect to the Fraunhofer case, if we think about an aperture and the light coming through an aperture, or sorry, the waves coming through an aperture, if you think about Huygens principle, where you can look at each point on the aperture, then you have this, you can sum up all the waves as they go at some location on the back focal plane. I'm just going to pause this for a second. Somebody was just snow blowing my driveway there. I just went out to thank him. Okay, get back to it because I don't want to finish. It gets too choppy if I keep interrupting this. The optics of apertures and in an electron microscope rely on superposition. So if one applies the Huygens principle and splits up each point across an aperture and considers each point as a source of waves which are emitted radially, then at a given angle on some plane, you can choose this plane any way you want, at some point you get a distribution of intensities, and that distribution of intensities reflects the superposition of the waves because of the different path lengths that they take. If we can consider the direct superposition from which would be the case in X-ray diffraction, we could think about this in X-ray diffraction, although this would be a very large angular range and we'd be sampling the intensities. But when it comes to electron microscopy, we're making use of lenses, and what we're basically doing is by using a lens, we can focus rays that are coming off at the same angle, and it gives you the same answer in effect, and focus them to a point on the back focal plane at the imaging plane where we see a diffraction pattern, and that is that's one of the benefits of using the lenses in an electron microscope. We can reduce the range, if you like, the angular range. We can select waves that are coming out at specific angles. It turns out to be very similar to or essentially the same as what you have here for if you don't have a lens in the place. But thinking about just simply, one can use any kind of MathCAD or MATLAB and reproduce this very easily. You just simply split up your length between the edges of the aperture, assign each point as a source, and then sum up the intensities where they superimpose at some different point. And when you do that, you get some kind of distribution depending on where you are relative to this aperture. So you move this line closer or further, and what you do is you see oscillations. Well, you see a difference in the distribution of the intensity as you get closer, but this what you find is that as you move this plane where you're sampling, this peak actually will oscillate between negative and positive, because you can see how you get into conditions of destructive interference at certain points. Or these peaks certainly would oscillate between that. So, I've just said that. So this is what I'm talking about. Just we're taking taking different points within the aperture, look at the distance, and then simulate what that would mean in terms of a superposition of the waves at each given point. So these are essentially the diffracted waves, and this is the direct beam. So when it comes to Fresnel imaging, so where this effect becomes important, I mean, the Fraunhofer effect is not such a big deal. We don't care about it too much when it comes to the far field because we already know that the diffraction pattern is simply a representation of reciprocal space. But when it comes to the near field imaging, we use the Fraunhofer effect, we have to consider the Fraunhofer effect. What do I mean by that? If we're looking at cavities, we can consider them as small holes or small apertures through which you have through which you're shining your radiation. So we're doing that, and we've got this got these cavities, and we're looking at the distribution of the intensity at some location away from in front of the aperture. And if we vary the distance slightly, like a fraction of a nanometer, in this particular case, we go from a condition where we have a bright peak, like here, or a bright image, or a dark image, as we have here. And at the point of focus, if you like, there is very little intensity. Now, this is useful to some extent if you're looking at small cavities, because it might make it easier then to see the cavities. If you go through focus, you can see these points going from bright to dark. But a word of caution: contamination on the surface looks the same as cavities. So here's some pictures from 2.5 niobium pressure tubing. Zirconium alloys don't have cavities, or very rarely, especially 2.5 niobium pressure tubing, because zirconium doesn't produce helium, and we don't have the conditions, certainly in reactor operation, we don't have the conditions to create cavities during irradiation. But when you polish the sample, you often leave residue on the surface, contamination. In this case, it's kind of like an amorphous niobium-rich oxide. And this shows up with Fresnel contrast. So this is a surface deposit. And we have the same Fresnel contrast, and you can see that this isn't a cavity, it's a little string of something, a little wormy structure. These wormy structures exist from the contamination and would show up bright or dark, depending. Now, the more circular ones, which you might mistake for a cavity, also show up in the same vein as bright or dark. Now, the reason that there are two points here. One, if one is examining a material and one looks at that and you say, oh, Fresnel contrast, this is a cavity in the material. Not necessarily. Especially if you see it as in a wormy kind of structure like this. Not necessarily. It is more than likely contamination in cases where you don't expect cavities. So if you have a sample and you say, oh, I don't expect to see a cavity, and there is this thing that looks like a cavity, check it out, do some stereomicroscopy, and verify for yourself that this is within the foil and not on the surface. So I've used this effect to some value, or in the past, during my studies on zirconium pressure tubing. This is an irradiated piece of zirconium pressure tubing, and during irradiation, the niobium itself forms clusters, small precipitates, and for whatever reason, let's say I'm interested in these precipitates I know what they are and how they formed. So in this field, in these two fields, I can see which ones are the precipitates, which are these black spots. So if we're looking at these black spots here, I can see which ones are precipitates because they're also black spots when imaged up here. They may be a bit fuzzy because we've gone through focus, but let's say this example here, it's black and black, and here's two black and black. Although you're essentially not focusing on these points in this particular case, these are beta niobium precipitates, and they're not contamination. They're not surface contamination. So I've seen so many instances in publications where people see these white dots and say, oh, look, this is Fresnel contrast. We do it through focus imaging, therefore it's a cavity. No, it could be surface contamination. So when you know you have cavities, Fresnel contrast comes into play when you're going through focus in understanding the variation in the focus in a regular image. So here's some cavities, real cavities or helium bubbles in an irradiated Inconel X750 sample. Now I can see the effect of the height difference of these bubbles within the foil, which just by varying the height at a certain focus condition in your microscope, the images might be dark and bright or bright and dark, depending on the height of these bubbles. So without resorting to stereo microscopy, I know I can decide at what height some of these bubbles are, like all the ones that are dark in this image are at one height within the foil, and all the ones that are dark in this image are at a different height within the foil. So we can use that Fresnel imaging technique to better understand the relative spacing or the relative distribution of real cavities within a foil. Keeping on with the optics now, when it comes to resolution, let's consider depth of field. And I'm going to diverge a little bit from the TEM and talk about some SEM. So SEM images are shown here. This is of the same material. This is Inconel X750. This is the unirradiated case, and this is the irradiated case. So because all those bubbles they're helium-filled bubbles, and helium doesn't get absorbed by grain boundaries. It tends to sit on grain boundaries and stabilize cavities there. You tend to get more intergranular, or a lot more intergranular fracture when you have helium bubbles in a material. Now, in this particular case, there's the image is quite nicely focused here, but it's a little bit fuzzy off to the edges. And partly that is because it has a different height. And depth of field becomes important. Now, in an SEM, the image quality or the resolution of the image is dictated by the spot size, so where it intersects the surface. So when you have a small spot size, let's say that hits the surface at this point, we see a smaller sampling of the surface. And when you have a large spot size and you have a variation in the surface height, for instance, this will become less resolved, this variation. So, and there's a range over which you say, well, we can tolerate this amount of resolution difference. And this is what's defined as a depth of field. Depends on the working distance and the aperture size and the magnification, of course. So depth of field, or the resolution is related in part to the focusing ability of the electron optics and getting a small beam, but also it's limited by diffraction effects. So as we showed earlier, we have this peak which shows up from Fraunhofer or even Fresnel diffraction, more the Fraunhofer, whether you have a lens or not, and the peak has a certain width depending on the aperture size. So if we take the semi-angle, convergence angle, which is dictated by the aperture size, and because it's a diffraction effect, there's a limitation on the width of that. The peak one would get, the interference peak, given by the wavelength. There's a limitation then in the resolution as one changes in this case the aperture size. So because we're limited by other things other than diffraction in the SEM, typically the resolution, or if you like, the probe diameter, varies in this range. Now, when it comes to the TEM, the resolution is very much dictated by this line and by diffraction effects. And I'll explain that in a second. So what dictates the resolution in an electron microscope is this Fraunhofer diffraction, where we have a peak width, and the peak width is a function of both the wavelength, amongst other things, but also the aperture. So we have a large aperture, reciprocity comes into play, just as it does with the plane with Bragg diffraction, where we have this reciprocal space where it's the diffraction pattern is the Fourier transform of real space. The peak width here is a Fourier transform of the aperture, and it's small when the aperture is big, and it's large when the aperture is small. And so we want a large aperture for high resolution to image atoms, typically in the electron microscope. The resolution limit is not dictated necessarily by the width of this peak, but by being able to distinguish, when you have overlapping peaks, what is the minimum separation that one can tolerate, where we can still distinguish between these peaks. And that's the expression that dictates this resolution limit is 0.61 times lambda over beta, where beta is the semi-angle of the collection angle of the aperture. Okay, so now we get into the theory. This will be the last part. I introduced, certainly for the case of structure factors, in order to calculate structure factors, that the wave is typically represented by this Euler number. Now, from an academic point of view, the phase, if you like, is some function of the frequency times time, and the distance times some value here, which is a measure of the wavelength or the phase of the wave, and that is 2 pi over lambda. Now, when we talk about electron microscopy, we have a coherent beam of electrons illuminating the sample the whole time. And if you can think about it in terms of a strobe effect, we constantly have this coherent beam which is just there. So in terms of time dependence of the wave, we don't have to worry about it. We're looking at essentially a standing wave, although it's not standing. If you think of it in terms of a strobe, it's a static condition. And so we can forget that. So typically when it comes to electron diffraction and understanding the diffraction effects mathematically, we're generally only interested in wave number or the wave vector, this k, and the distance. Distance in this case simply being the height within the crystal. What can approximate, even though we're talking about vectors, when it comes down to it, we're only interested in the height, which we call z. So formally, the wave equation describing the amplitude of the electron in the crystal is given by this. It's a sum of the direct wave amplitude and the scattered wave amplitude. So wherever you are in the crystal, you're going to be sampling a bit of both, especially if you're thinking about a column. And why are you doing that? Why would you, even though this is a direct beam, if you like, and a diffracted beam, why do you think of them as being coupled? Because they are coupled. Well, I mentioned in X-ray diffraction how one could think of the diffraction as simply single scattering events. So when an X-ray photon is interacting with an atom and it gets scattered, that's it. Right? You then think about where the X-ray ends up and what the phase of the photon is at the point at which it's detected compared to other photons coming in. In an electron microscope, in a material with electron diffraction, it's slightly different because, well, it's a lot different because the electrons interact so strongly with the crystal that when they're diffracted, they can all then rediffract and then interfere with the direct beam. So what actually happens is that you end up with a coupling of the diffracted wave and the direct wave. So this is the wave amplitudes here are represented by phi, and the wave equation or the phase is represented by this Euler equation here. In this particular case, the deviation from the Bragg condition is represented by Sz. Z is a distance in real space going down the crystal, and S is a distance in reciprocal space, which is the deviation from the diffraction condition. That is the deviation of the diffracting vector of a normal plane and the Ewald sphere. G and R in this case are an additional phase shift caused by distortions in the crystal. It can either come from a stacking fault or a dislocation. So it's the same kind of relation that occurs when you're building up a structure factor based on the position of the atom within a unit cell. But in this particular case, we've already dealt with that. We're already considering that we've got a strong diffracted wave where all of that is taken into account. And then we're looking at other effects now. So deviation from the Bragg condition, as said, and the effect of defects, which in fact change the deviation from the Bragg condition. So, but introduce a phase factor. Now, one of the early attempts to describe this coupling is by representing the diffracted wave amplitude as a combination of the diffracted wave amplitude and some diffracting vector, so that there's some component of the diffracted wave there's some component of the diffracted wave that feeds back in to the diffracted waves, but there's also the direct wave which feeds into the scattered wave. So this dphi g by dz, in this context, relative to the configuration we see here, you'll notice that each component is the denominator. There's this parameter called psi g or psi 0, and this is an extinction length. And this defines the distance in the crystal that the electron is traveling, where you might get complete diffraction. Sorry, it actually corresponds to a oscillation in the intensity of which is a full cycle. So we're going from a bright image to a dark contrast, bright to dark to bright. So this intensity will vary down the crystal. And when there's a maximum amount of intensity which is scattered from the direct wave, we've actually traveled half of an extinction distance. So this extinction distance is a measure of how far the electron travels before it's completely being scattered into some other feature. But then it comes back because of the coupling with the diffracted beam. So you can see how, if we look at dphi, the change in the amplitude, let's say of the direct beam or the scattered beam, the change in the amplitude is if you like, is dz over psi g. It happens over a certain distance where you get a change for whatever reason. You get some change in the amplitude because of diffraction effects which are dictated by, and the distance over which this occurs, like say 100% distance is psi g, and dz says what fraction of this 1 over psi g we're considering at each step as we proceed down the crystal, through the crystal. Now it turns out that when Howie-Whelan, Nicholson, and Pashley wrote their book, in it they make the point that they can't get this equation to work. It doesn't give the variation in electron intensity as a function of either deviation parameter or distance in the crystal, or that one would observe. So it didn't match observations, and it didn't lend itself to easy solutions. And what they found was that they could get agreement with the observations by applying a modification to this, and this is the modification that they applied. They, in effect, split the amplitude into a real and an imaginary part of different amplitude, of different amplitudes, because you have different extinction lengths that are in the imaginary component. So they found that they had to do this in order to get the agreement with what's observed. And what are we talking about? What's observed is the variation in the intensity as you go down the crystal for different combinations of these extinction distances, and also the variation as one moves between S positive and S negative. So, and this is directly from Hirsch, Howie-Whelan, Nicholson, and Pashley. In order to solve the equation, what they did is they made some substitutions, some phase shifts to simplify the solution, and they ended up by simplifying these equations into this form in terms of the Howie-Whelan equations, but the Howie-Whelan Nextland-Paschly equation, it becomes in a simpler form like this. You'll notice that the S and the deviation from G, or the scattering effect of defects, dislocations, and stacking faults, it's not, when you make these substitutions, it's extracted from the exponential form, and it just becomes a multiplier in this particular case to some new wave amplitude. So taking this equation, we then want to look at the solution to this equation, and you can do this numerically. So in my case, I used MathCAD. I plugged it into a Runge-Kutta routine. Oh, look at that. This is cut off here. Where this array here represents the starting conditions for the real part of the direct beam, the imaginary part of the direct beam, the real part of the diffracted beam, and the imaginary part of the diffracted beam. And within MathCAD, there is the Runge-Kutta routine. Using the Runge-Kutta method allows one to step through, take incremental, if you like, an iteration, change the dz, change the depth a little bit, and then calculate at each point a new factor which feeds into this array. And but how these different components, the real imaginary parts, how they change depends on the other entries. The real, we have the real and imaginary parts of the direct beam, and the real and imaginary parts of the diffracted beam. These parts contain the effect of the dislocation. In this particular case, sorry, I've included a dislocation, and this is the equation that defines what the rotation of the dislocation planes, the effect of the strain from the dislocation has on the phase factor. And here we have the deviation parameter. So when you do it this way, we can, and this is for a simple case of a screw dislocation. And that's in Howie-Whelan, Nicholson-Paschly. So anyway, you can solve those equations numerically, not analytically, numerically, and get something like this. So these are the two cases, S negative, S positive, just with some random selection of parameters which seem to work. And then if I put in a dislocation at the location 50 units in the thickness, this is an arbitrary length scale, 0 to 100 units, we see the effect on the scattered intensity. So that's one way to do this, the solution to the equation. But as I mentioned earlier, the one could think of the waves, or the wave amplitudes for both the direct beam and for the scattered beam as being like a standing wave, or a wave which is, you turn the strobe on and you're freezing it. So the time is factors out, and we're just looking at the distance. But in doing that, we can come up to a solution because it's a static solution for those wave equations. Now it turns out for the defect-free, let's not complicate it now, it's for the defect-free case where there's no dislocations or stacking faults. By manipulation, by substitution of the Hersh-Howie equations, it's possible to create a differential equation for each wave, for the amplitude of the direct wave and for the amplitude of the scattered wave. And these equations are analogous to what you would get from a coupled oscillator. And basically, because it's essentially somewhat like a coupled oscillator, you have a wave coming in, some gets scattered, some doesn't, some gets diffracted, some of that diffracted wave gets scattered and some doesn't. And then you look at down this column, you approximate to look at what the effect of varying Z has on the amplitude of these things. In Williams and Carter, and I think the same also applies to Hersh, Howie, and Whelan, they use the ansatz method to solve these equations. They use basically a complex exponential. They assume that this wave vector is now a complex exponential. And that gives two solutions for each oscillator. So we can think of it pictorial like this. Here's a coupled oscillators. I pulled this off the internet. And you can see how if we think about a direct wave and the diffracted wave, and they're going down through the crystal. This is as a function of time, but in our case, it was a function of distance in the crystal. These waves are sharing energy back and forward, and the amplitude is varying accordingly. And that's the coupling. That's the coupling effect. Now, this is a mechanical oscillator, coupling of a mechanical oscillator, and it's not quite so simple for us in diffraction because we have these scattering events which change the phase, and it's not exactly like this. On top of that, the other complication is refraction. Now, when electrons are passing through a material, some of them may be slowed down by the repulsion from other electrons, and that slowing down reduces their wavelength, increases their wave vector. But some of them may be speeded up when they're attracted by the atomic nuclei. So what you end up with is the possibilities of getting two waves. Well, sorry, I shouldn't say two waves. Yes, two waves. And you can think of that in terms of if you how these waves would then interact, the one being slowed down and the one being speeded up. We also then end up, if you superimpose two waves which have slightly different wavelengths, you end up with somewhat similar to this, a situation like this, for which there are two solutions for the wave equation. So you're essentially plugging this thing into that and coming up with a more complicated result. So while a pair of coupled harmonic oscillators serve as a good mechanical analog for kinematical electron diffraction, I didn't mention that it was kinematical, but that's single events, if you like. Dynamical, actually, I'm not even sure that that's correct. Let's just say it's a reasonable mechanical analog. Dynamical diffraction is complicated due to dispersion, because the electrons entering the crystal are scattered, refracted in two possible ways. The electrons are either decelerated or accelerated by the potentials in the crystal. The direct and diffracted waves are then the result of interference of the two resultant waves of different wavelengths. I didn't do a lot with optics when I was a student, but there are some things that one can look up from textbooks on optics or waves. Ignore the top one, which is in frequency space, but this one's now, if you look at this bottom plot in wave space, there's when two waves are superimposed and they're close in wavelength, there's a in terms of the this is an absorption curve, where you can get this. I'm not sure what the absorption is here, but the refraction effect of the waves as we get close to one is shown here, and this shows that you get more absorption here, or destructive interference, and more constructive interference here. But there is a change in the refractive index. Sorry, this is N now. Change in the refractive index, which is negative when the one wave is slightly shorter wavelength than the other, and positive when one wave is slightly higher than the other. And this is known as anomalous dispersion in the one case, and regular dispersion in the other case. So in a non-dispersive medium, or if we're thinking about kinematical electron diffraction, we don't consider the formation of anything of these refracted waves. There's no refraction and weak scattering. And this is how the diffracting vectors would be envisaged in an Ewald sphere construction. You have a beam represented by a wave vector, which is 1 over the wavelength, and then it's diffracted. And the difference between the two beams is the diffracting vector G. Not to assimilate there. But when we think about dispersion, there are two possible waves now. We've created this slowed wave, which has a shorter wavelength, and in terms of the reciprocal space, this amounts to a larger vector for both the direct and the diffracted beam. We have a larger vector than what would be the case for the kinematical case, where you have no dispersion. So these two waves, when you're close to Bragg, are coupled, and we have an interaction. So we have a number of possibilities. We got the direct, so the refracted, what's called a block wave 1, refracted block wave 2 in the direct beam, and then the same, but with this deviation from the diffraction effect, the diffracting vector of G in the diffracted case, which then are summed up, superimposed to give what would be the diffracted intensity. And likewise, if we were looking at the direct intensity, it's the sum of these two waves as they are selected on the backfocal plane of the microscope. So block waves are a natural consequence of refraction, but they're also a natural consequence of what Hirsch, Howie-Whelan, Nicholson, Paschally, how they formulated their equations. But remember, Hirsch and company, they had to assume some fudge to make the equations work with no physical relationship. It's just some way to make the equations give you the answer you want. And then when they work through the formulations, it turns out that they have to have two solutions to the wave equations, or multiple solutions. Two solutions for the direct beam and two solutions for the diffracted beam, which is exactly this. But that's what one would come up with anyway if one was just simply did a thought experiment and say, what do we have if when our wave coming into the crystal is refracted, but it's refracted into two parts? How do these different two parts then interact when it comes to this coupling effect of the direct beam and the diffracted beam? And this is a pictorial pictorial picture. Of course, it's a pictorial picture. This is the way to think of it in a non-mathematical term. But we end up with this anyway, or Hirsch and company ended up with this picture because they had to apply the fudge factors to make the equations work in the first place. So when I was first introduced to dispersion surfaces and this sort of thing, I didn't understand it. As a student, physics at Bristol University at the Royal Fort, we had a lecturer. His name was A.R. Lang, Professor A.R. Lang, and the first lecture we had where we were introduced to these things, he came in and he drew a circle on the board and he drew another circle on the board and said, there's a dispersion surface. And then he proceeded to just talk at the board for the next half an hour, mumbling something about dispersion and diffraction and whatever. And we were all scratching our heads. We go, what the heck is he talking about? And I've never really understood block waves until more recently. And then it occurred to me that, oh, we're talking about two real waves and they can be detected. And this is an image of a block wave, an electron diffraction that I pulled off the internet. They can be detected and they're real. There are real waves. And once you realize that they're real and they're not some imaginary number, then it becomes much more, or a fudge factor, if you like, then it becomes much more poignant and one can understand it and accept it much easier. And if I have to share anything with you, it's that. And I might be wrong. I could be completely out of my mind, but this is how I can rationalize it. The only way I can rationalize everything that Hirsch and company did and put it in, make it sort of make sense physically, is if I start off by thinking in terms of, well, we've got two possible waves here, or two refracted waves, and they can each interact both by being coupled to give a diffracted beam, and yeah, so we end up with this range of possible solutions. The block wave 1 is a larger wave vector. and that's a shorter wavelength because it's slowed by the medium. And block wave 2, which is this bottom one, has a smaller wavelength. It's a longer wavelength because it's accelerated by the medium. So how does this work out formally? Well, we go from representing, as I showed you initially, the wave equation in the crystal being represented by this. It's now represented by a sum of block waves with different multiplying factors. So the block we have different these amplitudes, if you like, are a function of the deviation parameters. But block wave 1, so for whether you talk about I should mention that this really is for, so block wave 1 is some combination of these diffracting conditions. Block wave 2 is given by that. So these are the solutions to the differential equations which were put together in order to fit the observations. Okay, so the two block waves have wavelengths which are greater and smaller than the incoming waves. I've mentioned that already, so I don't have to talk about that anymore. Okay, so finally, the last point I want to make is in textbooks, you'll see this kind of representation of the block waves. Block waves corresponding, in this case, it's the 1 and the 2 here. So we have block wave 1, which is the one that's slowed, and block wave 2, which is the one that's speeded up. So traditionally accepted, block wave 1 is the one that's absorbed the most for negative deviation from the Bragg condition. And it's generally assumed that's because this is the one that interacts with the atomic nuclei and is therefore more absorbed for this S-negative condition. While it's traditionally assumed that block wave 2 is the one traveling down between the atom nuclei. But I'm not so sure that this is the right picture. Is it correct? Well, according to what I just explained there, where I could think of block wave 2, which is the smaller wave vector and therefore larger wavelength, this would come about physically. You can envisage what block wave 2 is about by it being accelerated, and block wave 1 is the one that's decelerated when it comes into the crystal. So what I think is probably a better picture is this one is the one, block wave 2 is the one that's going close to the atomic nuclei and is being accelerated, but it's not being absorbed by the nuclei. I mean, the nuclei themselves, physically, the cross-section is very small. So it goes whizzing past, like a gravity assist, if you like. And we end up with little absorption, but we do get the slowing effect for block wave 2. Now, whereas block wave 1 is, let's say it's traveling through the electron cloud surrounding the atomic nuclei, and it is absorbed. The reason to think of this as being the more feasible picture, being absorbed, is absorption is a bit of a misnomer, because in the context of an electron microscope, if you have a big thick piece of material and you shine electrons through it, and the image is just basically dark, it's not because the electrons are all sopped up by the material. It's because the electrons are scattered out away from the optic axis. They're scattered into the sides of the microscope. So absorption in that context is really more scattering. And I could rationalize that in this picture simply by saying the nuclei are very small, and therefore you get less scattering, but more acceleration. But here, when the Bloch wave is traveling down between the planes of the atoms within the electron cloud, which is the bonding electrons, the valence electrons, and the bound electrons, and the bound electrons as well. Whatever, you've got a lot more events happening, a lot more scattering events, and therefore more absorption happening here. So we end up with these two equations, essentially that lead you to this picture of the two Bloch waves in the crystal. And that comes about because we had to make, or Hirsch and Company had to make certain assumptions about the equations and how they could manipulate them or reformulate them or make them agree with the experiment, so they become in effect empirical equations. So to finish now, I'm just going to read this. Electrons traveling in a crystal potential can be represented by simultaneous equations that are similar to the mechanical analog of coupled oscillators. This inevitably results in a solution for the two oscillators, the direct and diffracted waves. That is a combination of the two solutions for each quadratic equation derived for each oscillator. The coupled simultaneous equations describe what is observed and imply that there are two solutions, Bloch waves, that can be combined to describe the variations in amplitude of each oscillator. But which came first? If one looks at the equations that are formulated, we end up with two Bloch waves being the result. But which came first? Refraction acts on the direct and diffracted beams, producing two separate real electron waves that then travel through the crystal. The description of the total electron intensity is the function of scattering angle and distance traveled in terms of coupled equations follows. So you going at it from the reverse direction, you'd get the same answer. My math isn't good enough my brain hurts too much to to try and do that. But I'm just sharing with you a way I can rationalize this. It helps me understand what's going on. And when I just take things on faith, as I have had to do over many years, before I realize, oh, maybe these waves are actually real waves. Once I realize that for myself, I can accept this, and it doesn't frighten me anymore. So I like the idea of the two refracted waves, and I like the idea that we aim to that solution by two separate routes. In the one route, which is the one that I can handle, is the physical consideration of refraction, and the other route is by making these what in effect turns out to be empirical solutions to fit the observations. One ends up at the same picture, that you have to have in effect two waves for each wave vector in the crystal, one being the direct wave vector and the diffracted wave vector. They're each separated into two components, which are from Bloch wave 1 and Bloch wave 2. and you couple them all together, and by some further manipulation, you can rationalize what you get. I'm comfortable with that. Okay, so this came from a lecture I gave recently, which shows some. It's just some things from YouTube that I put together, showing slip and defects in crystals. But the bottom one here is of value because it's something I saw on YouTube, which explains the refraction, especially with electrons. So it's a good one. And that's all I have to say now. Thank you.